All right, so during class today, we did this first. I had them do this in groups, and then I will show that I had them do on their homework this question. You can look at the key, and I discussed it based off of yesterday's notes, and now it's go time. Of course, I'm not ready. I don't know where my pen's at. There it is. I am ready. Okay, so third hour, 2026. This video may be the rest of my career, so you guys are, you'll be there. My lovely third, right? We've had a great year together. All right, let's move on. Okay, tan of x. What are you laughing at? Okay, input, say it. Okay, we have got the chart. Let's stop doing it, all right? And then let's stop doing all of the values. Let's talk about the most important ones. And the most important ones that we're going to graph are these. Tan of 0 is 0. Think about the unit circle here. All right, so all we're doing is input outputting. Here's 0, which is 1 comma 0. Tan is y over x. That's how you get 0 over 1, which is 0. Okay, graphic. Okay, you don't have to make that noise. Tan of over 4s. I've just told you that with cotan. No, I did not. We didn't have one in our bell work. Darn it. In our bell work, we did not have a tan or a cotan of an over 4. That's a bummer. I wish I would have, because then I could reiterate how that's 1. I could use my hand. Here's over 4. It's root 2 over root 2. 1. Or if you write root 2 over 2 comma root 2 over 2 for the unit circle points, that equals 1 when you put sine over cosine, or the y over the x. So we're going to write that. Here's pi over 4, and we're going to call this 1. There's pi over 4 comma 1. Wrong, that's 1. This is pi over 4. And I do want you to write that in there, okay, because we do have to mark these critical values. All right, and then, oh no, tan of pi over 2, that's 0 comma 1. That's 1 over 0, which is undies. What always happens at undies, everyone? What happened yesterday with undies? Asymptote. And I don't want to bore you. I hope we get it. That when I plug in like a number really close to pi over 2 and I tan it, you're going to, you know what? Let's actually do it. Let's do it on the video. Let's be a mathematician. Okay, you don't have to get your calculator out. Apparently my computer's not, oh, if this doesn't work, I'm going to be so mad. I should not have to do this every time. This is on the video every time. I already went to tech and I thought I got this solved. Let's see if this opens now. Okay, let's get that closed. Let's try to open it again. Oh my goodness. Come on, let's do it. I knew this was going to happen. All right, we're fine. I guess it wasn't the worst. Hey, first things first, make sure your calculator's in radian, but you didn't get it out. Okay, next thing is second quit. And I don't know if this is going to help you or not, but I'm still going to do it. It should be something that gets in your brain. I realize when I do my video this way, the microphone can't really hear me when I talk away from it. So I got to yell. Here's pi divided by 2. Shh. Okay, boom. So you know what I'm going to tan? I'm going to tan 1.57. Stop. That's right before the asymptote. Okay, so tan 1.57 radians, short of where the asymptote's located. Booyah! 1,255. All right, and that should be enough for you to understand that right before this asymptote, this sucker's way up here. So the graph behaves like this. That's why we have an asymptote there. When I tan pi over 2, the calculator will shut down. The fatter math, I'll do that. I'm typing on the screen. I think I hit it. There we go. Here's tan of actually pi over 2. Sorry, I can't find the tan button. And then let's put it in exactly divided by 2. That proves the undefined. Their domain issue. You can't have 0 in the denominator is what the calculator's reading there. But right before that, huge output. So that's enough to make you understand the asymptotic behavior of the graph. Right? All right. And then let's go backwards here. That's in quadrant 4. So tan of a quadrant 4 angle measure is negative, and that's how I get -1. So here's -1. And then tan of negative pi over 2 is an asymptote. Okay, now I'm going to ask you to stretch. Again, you don't have to do this when you're graphing. We like to tell you where these values come from. And then we lock in on attributes. This is what tangent looks like. This is it right here. Okay, because then the next iteration of this goes to 3 pi over 2. At 3 pi over 2, tangent is also undefined because this is 0, -1, y over x, if you were looking off to the left. And then what happens at pi? Tangent of pi is 1. So this happens again. I'm sorry, 0. I said that wrong. This is -1 comma 0, and this is 0 over -1. And then these over 4 values, you get -1 and +1. This is in quadrant 2. This is in quadrant 3. That's why we get, quadrant 3 gives me positive ratios for the over 4 values. So it copies and pastes. We can see that this is periodic. And then guess what happens at -3 pi over 2? The same thing that happens at pi over 2 because those are in the same spot on the unit circle. What happens at -pi? Same thing that happens at pi because they're at the same spot of the unit circle. And I think we get how periodic works. So there's your tangent function. There's 3 periods worth because those are all copies and pastes of each other. So what is that period? From this distance to this distance, that's a period of pi. Highlight that. We got a problem now. Sine, cosine, secant, and cosecant all have periods of 2 pi. But tangent has a period of pi. So any future periods are going to be pi over b, not 2 pi. This has got to be a memorization factor in your mind, or else you're doomed and you will constantly miss these questions. The fat or mac, the same thing happens with cotan. Fine, we're going to go ahead and fill this out. What's the cotan of 0? That's 1, 0. Cotan is x over y. Oh no. I start with undies right away. That means I start with an asymptote. You know what I'm going to do? I'm going to go to all the quadrantals. Again, you should know what that word is. I almost use it every day now. The quadrantals are the x, y axis values. Okay, but now x over y is 0 over 1, which is 0. So that's where I have a 0. And then what happens at the over 4s? Cotan of pi over 4 in quadrant 1 is 1. Because it's just the flip of 1, what I got for tangent. Tangent of over 4 is 1. Pi over 4. Cotan of pi over 4 is also 1. But then in quadrant 2, and I should write that, that's pi over 4. Put that in there. 3 pi over 4, that's in quadrant 2. That gets me a -1. And then at pi, you get -1, comma 0. That is x over y. -1 over 0, which is an asymptote. So cotangent is just a little bit different. Actually, students like cotangent better than tan because the first asymptote is the y-axis. The second asymptote is the period. So it's a lot easier. Tangent, you're going to have to remember that the first point is 0, 0, and then half the period to the right and half the period to the left is where the asymptotes are. So lock it in. I saw somebody shake their head. Yes. Hopefully they got it locked in. Everyone else has to. All right. We got to get it done. This is the, extrapolation. We plug in the points, we get a pattern, then we lock in the pattern. You can't lock it in if we don't, wax on, wax off, do your homework, and all that other stuff. Pi over 2 and -pi over 2, you get 0. All right. I don't want to bore you on this. I think you get the idea. You're going to get a repeat over here. This is the period, so I should get a repeat over here. We don't have the input-output anymore. And I'm going to stop there. Now you're going to keep filling out the chart. I filled out the chart for 1 period's worth. The rest happens. Okay, so look at this and maybe really highlight these things. Cotan and tan have the same period, so therefore future periods of cotan and tan have to be pi over b, not 2 pi, because it's compared to the parent. And then really lock in on what the problem with tangent is. It's the same problem with secant. Secant's asymptotes don't start at the y-axis, but just graph for secant cosine, you'll see that, and don't really make a big deal out of it. And then how far are the asymptotes away from each other? Actually, a period away. That's why we have pi k there. Why can I just do pi k for cotan? Because the first asymptote is 0. When I plug in 0 for k, I get 0. X equals 0. When I plug in 1, I get x equals 1 pi, which is where the other asymptote is. When I plug in -1, we can see that asymptote right there. I'll color it in green. So that's how that works for that one. All right, then one thing to remember, tangent increases, cotangent decreases. All right, and we're good to go. Okay, so you know what I'm going to do? We're going to go right here, and we're just going to get the brass tacks of this all. We're going to graph, you know what I'm going to do? Stick this in here. Stick this as a tan bx, right? So that's like how we're going to work all of these. And I might throw in a phase shift, right? But I don't know if I want to graph with the phase shift yet. I'll check the homework. Might be a quick jump. We're going to spend one more day tomorrow graphing both. I might have you up on the boards too a little bit, then just let you work. All right, so here's how you break down tangent. 1, 2, 1, 2. Without a phase shift, 0, 0 is a point because tangent of 0 is 0, input, output. So that's the problem with tangent. It starts with 0, 0 as a point, and then you have to go half of the period to the right. So put a half pi over b, because the period is pi over b. That's the difference between the other 4 functions. That's not a 6. That's a b. That's a b. That's a b. Okay, so that's how I find the period. But this mark right here is half of that. Half the period to the right, asymptotes, and then half the period to the left, asymptote. And the period is pi over b. So we'll deal with those fractions here in a moment, and then I'll hold off on finding this one. This is 1/4 of the period, but we'll just take half of that value and mark that. All right, so whatever this is, when we have an actual question, just take half of it again. It's the same math as sine and cosine. But then this a value, we cannot, oh, I'm sorry, we cannot call this an amplitude, but we do need it as an a value for a stretch shrink factor. Whoa, did you hear that whistle? All right. So, yeah, we can't call it an amplitude because amplitude implies a high-low point in our range, and it doesn't go any higher or lower than that. This goes on forever. It's a Federmact. I can do this. What is the range for both tangent, cotangent? All real numbers just on this graph alone. Every single y value is covered because this goes forever up and forever down. The domain issues, though, are the asymptote issues, right? We can do that when we actually work with one. Here's why you're going to love cotan. Cotan, unless it's phase shifted, starts with an asymptote and ends with an asymptote. And what is that asymptote? Whatever the period is. So that's why cotan you're going to love. Oh, and then by the way, put an A cotan B there. You know, just like we had with sine and cosine, it was A sine bx, A cosine bx. And then this is halfway, and then that's where the 0 is, and then we do have to cut this in fourths. I'm going to wait on that. We'll actually get numerical values and wait to, deal with these fractions. Here's the problem, though. This is in quadrant 1, so that's a positive. This is in quadrant 2, so this is where the negative happens. Cotan decreases as a graph, right? Okay, so that's where we get to lock in. First thing we got to look at is what am I dealing with, cotan or tan? So which one do I have? And then I got to break down the numbers. And the breaking down the numbers is the exact same as like sine and cosine. So we're going to do this one on our little old coordinate plane I used to use back in the day. These are some of my old notes. Okay, so amplitude, write this down. What is the amplitude? Just like in secant and cosecant, you cannot say there's an amplitude. So say none. We're going to be jerks. We're going to ask, what's the amplitude? And we're going to try to trick you. We're going to do it. I'm sorry. I'm just being honest. At least I'm informing you. The period, though, is 2 pi over 3. Okay. So, but I'm dealing with a tan. So this is what you got to understand. And I could prove this by input output, but I don't want to bore you. But that's would be nice if we, would investigate that. So what I have to do for tan is go this way and this way. And by the way, when I plug in 0, 3 times 0 is 0. Tan of 0 is still 0. That's why 0, 0 is a point. So that's number one. What's the matter? You're right. I'm a maroon. Oh my gosh. Got too many things. Nicely done. Group over there. Well done. High over B. I'm a maroon. I made a mistake. All right. But back to if I plugged in 0 for X. 3 times 0 is still 0. Tan of 0 is still 0. You still get 0, 0 as a point. That would only change if there's a phase shift. We're going to hold off on that. All right. Now, what's half of pi over 3? What's half of pi over 3? Everyone should know that answer. You drive me nuts by not answering that very quick. Pi over 6. You just those people that are still struggling. Take the denominator and multiply it by 2. You're killing me. You frustrate me. I lose sleep at night thinking about you people that are fractionally challenged so bad that you can't take 2 times the denominator. So now I'm going to ask you again, what's half of pi over 6? Pi over 12. It ain't rocket science. Okay? And then that's negative pi over 12. So that's why I waited. I don't want to fractionally break it down up in that one. You know how to do this work. You should. That's why I'm frustrated with some of you. 1, 2. This is the 1, 2 value. So it is a stretch. That's what happens when I plug in pi over 12. Fine, I'll bore you. When I plug in pi over 12, 3 times pi over 12 is pi over 4. I'm going to say that one more time. When I plug in pi over 12, 3 times pi over 12 is pi over 4. Tan of pi over 4 is 1. But what's 1 times 2? Input, output. I just did it. And then negative pi over 12 gives me that negative pi over 4 in this position. Tan of negative pi over 4 is negative 1 times 2. That's why we get negative 2 here. So A is a stretch factor. And then if I was mean and I said do another period, then I would say go right. It's the same math as sine and cosine. 1 pi over 12. Let's all do it together. Third hour. Let's listen if they actually answer. 1 pi over 12. Come on, this is the rest of my career. They're going to hear how third hour was in 2026. So let's start over. 1 pi over 12. What's next? 2 pi over 12. What's after that? 3 pi. Well, hey, hold on. 3 pi over 12 isn't that pi over 4? I was never good at math. It was my worst subject. Is that right? 4 pi over 12. What's 4 pi over 12, everyone? Pi over 3. 5 pi over 12. What's 5 pi over 12? 5 pi over 12. 6 pi over 12. What's 6 pi over 12? What's 6 pi over 12? Pi over 2. Why did I have to go that far? Because I need another asymptote. I need another 0. I need another negative 2 value and another 2 value. So it's the same math that we had for sine and cosine, and now actually secant and cosecant. So we should be able to do 2 periods worth. All right, now get rid of this. What time is it right now? Nice. Okay, now watch this. Now I thought I'd throw this in here. Input, say it one more time. Output, third hour. Nice. Okay, over the interval 0 to 2 pi. You know what? Forget that. I think I changed that last year. We're only at pi over 2 right now. So let's just say that interval from here to here. Over this interval that I just drew 2 periods worth, but I even cut this one off. Just from here to here, where is f of x greater than 0? What's greater than 0? You've already been asked this when we did rational functions. Above or below? Above. So it's these parts of the graph that satisfy this equation. All I have to do is name the intervals that this happens. All right, look at this. It says equal to 0, and 0 is a solution. So it's from 0 here to pi over 6. So it's these intervals, right? Inputs, these inputs, and these inputs. All right? So those are the ones that satisfy this particular set of directions. All right, so I just thought I'd throw this in there because we've already been asked these questions. Hey, pi over 6 is an asymptote. Do I put a bracket on that? Yes or no? No. Why? What happens? Thanks for answering, though. I do appreciate that. No one else said anything. Why is it not why is it not? Because it's a what? And it starts with an A, asymptote, and that means the graph is what at that position? Starts with a U, undefined. Asymptotes are never solutions to inequality questions, ever. You've actually done this before. This was in rational function graphs. Then we'd ask you inequality questions after that. And then it's from pi over 3, which is a 0, to that last asymptote, pi over 2, which cannot be included. So I did change that because to 2 pi, this goes forever. There's like 4 more, actually 2, 4, 6, 8 total tangent graphs if that occurs. Then I'm going to just do this one. Where are we at here? 57? Good. We got to get going. All right, you're right. I made that mistake before. This is pi over 4 as a period, not 2 pi over 4. So the period is pi over 4, but it's a cotan. We love cotan. But what happens to this cotan? What happened with this minus 1? What does that do to the graph? Sucks it what? Down 1, right? So I need a new negative 1 value here. But then this 2 is a multiplier. So I go 2 up from this, 1, 2, and I mark 1 as a critical value, and 2 down from this, negative 3 as a critical value. This might be a stretch, but it's not that bad. We know about up-down shifts. I want to stay away from phase shifts for a minute. I might try it on the bottom part here. I'm running out of time, so I may not answer this inequality. Just do it if you want. It's coming up, so I just wanted to maybe throw that in there. Okay, now here comes your memorization factor. What happens with cotan? Well, first of all, when I plug in 0 here, 0 times 4 is still 0. Cotan of 0 is still undefined. So what do I have at 0? Starts with an A, everyone. Asymptote. So just lock it in. All right. And then the period is pi over 4. So just do it. This is the same as sine and cosine. And then what I have to do is cut it in half. Half of pi over 4 is pi over 8. Half of pi over 8 is pi over 16. Oh, these are going to be in the way. Oh, well. 1 pi over 16, 2 pi over 16, 3 pi over 16. I do have to put that up here. They're going to be in the way of this graph. 4 pi over 16. If you still don't know how to break this into fourths, that's why you failed the sine cosine test. I can't keep teaching things. You guys have got to lock in, some of you. All right, but then here's what happens with cotan. It's easy, actually. This represents the quadrant 1 answer. So that's the positive high points. This actually represents a 0, but it's been moved down 1. That's why I was afraid I was going to run into my angle measure with the graph. Then this represents the quadrant 2 answer, which is the negative answer. Or just remember, cotan decreases, not increases. And then for this, you can just cut and paste and copy it over here. This is why you're going to love cotan. Cotan's a lot easier. Negative pi over 16, negative pi over 8, negative 3 pi over 16, negative pi over 4. Then we'll hold off on that. All right, then the last couple, and this is the same thing I did last year. I only got to do one of these. It does say do a tan and a cotan up there. So I do want to challenge you a little bit thinking about phase shifts and flips. First of all, who does this look like? Tan or cotan? Who decreases? Tan. So cotan does. So to make this a tan, what would I have to add in front of it? A negative, so a flipper. All right, and then where are we at? Here is the 0, 0 value. So this is not phase shifted, but it is a negative cotan because it is upside down. Now concentrate on this 2 right here. When I graph this here and here, this looks like it's at 1 and negative 1. So it is a 1 tan. You don't need to write the 1, but we could do that. And then I think, we got to do the period. Wrong. I'm a buffoon. Okay, I'm a buffoon. Hey, I see this. This is pi over 4 right here. So what's this right here where that asymptote is? Pi over 8. But here's the problem. This is pi over 8. That makes this negative pi over 8. How far are these away from each other? How far is pi over 8 to negative pi over 8? Pi over 4. It's right there. You got it. So the period is pi over 4. Remember, b comes from pi over p. We could switch these two, all right? And therefore, I could put b equals pi over 4, because that is what the period is. That turns into 4, all right? Or, I mean, come on, the period comes from pi over b. B staring you in the face. It's 4. B is 4, all right? So therefore, this answer is -1 tan 4x. That's my b value, because then pi over 4 is the period. So it all worked out. And I've done this math before. How do I handle pi divided by pi over 4? You flip. Pi times 4 over pi, the pi's cancel, one way or the other. Now, to make this a cotan, wouldn't you agree all I have to do is phase shift this right, pi over 8, right? Okay, so to make it a cotan, it's just y equals a positive cotan, same period value, but then shifted pi over 4, actually either to the right or the left, not pi over 4, pi over 8, but I chose right. And that's really the only thing I really care about phase shifting, maybe. Writing a new equation in terms of cotan. Why positive? Because that's how cotan looks, it decreases. All right, so do the best you can on these notes. We're going to spend a couple more days on graphing, at least one more. Tomorrow we'll try to clean up. Yeah, and that's it.